This is problem 47 from Matter Waves. We're going to use this problem when we do the virtual pair production lab. And this came from the virtual pair production lab where we have Heisenberg's uncertainty principle allows for short-term violations of the law of energy conservation if delta E is the energy which is borrowed from empty space and delta T is the elapsed time before the energy must be repaid, then delta E times delta T is approximately equal to h bar over 2. So this is what we're using in problem 47, and you'll want to refer to this when you do the virtual pair production lab. So in problem 47, it says, empty space can never be completely empty. Particles can spontaneously pop into existence, dance around for a period of time, and then disappear. These virtual particles have huge repercussions on the structure and fate of the universe. Imagine an electron and a positron popping into existence. If each particle receives 100 kiloelectron volts of kinetic energy, determine the maximum distance each particle can travel before disappearing. So we have an electron and a positron. Those particles have the same rest energy. So delta E is equal to, and it says each particle receives 100 kiloelectron volts of energy. So for the two particles, we have twice the rest energy plus the kinetic energy. The kinetic energy in this problem is 100 kiloelectron volts. And for an electron and a positron, mc squared is equal to 511 kiloelectron volts. So delta E is equal to twice, because we have two particles, 511 kiloelectron volts plus 100 kiloelectron volts. So that is twice times 611 kiloelectron volts, which is 1222 kiloelectron volts. So now using Heisenberg's uncertainty principle, I want to calculate the maximum distance each particle can travel. So first I want to find delta T. So delta T is approximately equal to h bar divided by 2 divided by delta E, which is 1222 kiloelectron volts. You can look up h bar in the appendix in the back of your book. H bar is h divided by 2 pi. That's 0.658 times 10 to the negative 15th electron volts times seconds divided by 2 times 1222 kilo electron volts. Make sure you take care of the kilo here because you only have electron volts in the numerator. And that gives us delta T is equal to 2.69 times 10 to the negative 22 seconds. But I wanted to find the distance. In order to find the distance that the particle travels, I need to know what the velocity of the particle is. Okay, so this is the time before the energy has to be repaid. So this is how far it can travel before it disappears. And I need to find the velocity. In order to find the velocity, first I'm going to find gamma. I know the kinetic energy is related to the rest energy by gamma minus 1 times mc squared is equal to the kinetic energy. I know the kinetic energy and I know the rest energy. This is just for one particle. You can do it either for the electron or for the positron. We have gamma minus 1 is equal to kinetic energy is 100 kiloelectron volts, and mc squared is equal to 511 kiloelectron volts. That gives us 0.1957 with no units, and gamma is equal to 1.1957. If I know gamma, then I can find the velocity. I know gamma is equal to 1 over the square root of 1 minus v squared over c squared. And I've done this enough times where I feel like I don't have to do it all over again here. I can just say the velocity is equal to the square root of 1 minus 1 over gamma squared times c. So plugging in gamma, I can find the velocity. That's the square root of 1 minus 1 over 1.1957 squared times c, which is 0.548 times c. But we wanted to know how far the particle travels before it disappears. So this is the velocity, and it has a time of 2.69 times 10 to the negative 22 seconds that it can travel in. And so we just say distance is equal to the velocity times delta t. And so we get 0.548 c times 2.69 times 10 to the negative 22 seconds. And that gives us 4.42 times 10 to the negative 14th meters. So that's how far the electron can go, also how far the positron can go before disappearing.